inviting me. It's my second time in Sao Paulo, first time in 23, and I found out that it was a very nice city, and fortunately, it even has a very good dentist. But, but this time, hopefully, it will be much smoother. I'll tell you about QCD integrals meet gravity. More specifically, I'll focus on the fairly new field of post-Minkowskian corrections using quantum field theory. I'll start with some background, then I'll cover several aspects of Feynman integrals as relevant for the gravitational wave problem. Kinematic expansions, which is closely tied to classical expansions. Integration by parts, which allow us to write complicated integrals in terms of simpler integrals. And finally, how to evaluate these supposedly simple integrals, still not that simple, and using modern methods like differential equations and reverse unitarity. I don't need to mention to this audience that gravitational wave physics is proceeding is developing at a very rapid pace. We had 90 events combined from the 03, 01, 02, 03 runs of LIGO. And in the about 2 years of the 04 run, we already accumulated 254 events. And the story is going to continue. This is just one of the many signals detected by the 04 run. It reached a signal-to-noise ratio of around 80, which is about 3 times better than the first detection back in 2015. And there's a bright future ahead. Many planned detectors, ground-based, like LIGO A+, Einstein Telescope, Cosmic Explorer, and space-based ones like LISA, Tianqing, and Taiji. Depending on the frequency, especially in the low frequency bands, you are going to see orders of magnitudes of increase in the strain sensitivity going down this direction, detecting ever small strains. It will allow you to see far more sources, far back, much further back in time in the cosmological redshift. Surprisingly, in recent years, QFT methods changed the field. We know that we need accurate theoretical predictions to meet the challenge of future detectors. For example, in the SNOWMAS white paper, we estimated that up to the 7th order in G may be needed for the perturbative in-spiral regime. It's not the first time that QFT method has entered the field. Much earlier in this century, around 2005, NRGR, an effective field theory, which was motivated by HQET and NRQCD, was formulated to target the post-Newtonian expansion. More recently, there's the booming field of post-Minkowskian expansion, which naturally uses a relativistic QFT methods to obtain results with exact dependence on velocity. Rather remarkably, it produced most of the results beyond the second post-Minkowskian order, although there are also classical GR results by Damour and collaborators, mostly on certain pieces, certain radiative pieces that can be obtained by linear responses. And here's a slide I stole from Gustav Mogel from a few months ago, which summarizes partially some of the highlights of the advances in recent years, and the vast majority of them are powered by QFT methods, including both amplitude and world-time methods. There are many reasons why QFT methods worked so efficiently. I cannot really pin down exactly one reason. There are several. There's the inherent efficiency of on-shell methods, like generalized unitarity and double copy, the power of gauge invariant methods, like focusing on gauge independent scattering observables. We benefit from the top power of effective field theory and the magic of dimensional regularization. What I will focus on in this talk is importing the techniques of Feynman integral techniques developed in collider physics, especially perturbative QCD, because as we know, LHC is mainly a QCD machine, and at these high energies, protons are basically just gluons. So this is the focus of the talk, and it will be heavily biased towards amplitude-based approaches for the post-Minkowskian expansion, though I'll mention other exciting topics like world lines. First, I'll talk about kinematic expansions, which map the classical expansion, i.e. the h-bar expansion, to a kinematic expansion in amplitudes. So before I dive into the integrals in abstract, I have one last slide directly connected to physics, which is how you do the classical power counting. There are many equivalent methods which are completely equivalent and equally good. The most intuitive one would be directly counting h-bar. However, one of the ones I found to be natural is this counting with quantum numbers. It's an observation that in the classical limit, we have the correspondence limit, i.e. all the quantum numbers must become large. For example, this orbital angular momentum must be large in the units of h-bar. And assuming order 1 velocity, the momentum is similar to m. So the orbital angular momentum is similar to m times the radial separation r. Meanwhile, graviton exchanges controlled by this Fourier inverse h-bar over r. So we have m times r much greater than this h-bar, which leads to the parameter that q over m must be much smaller than 1. So the classical expansion has turned into a kinematic expansion of scattering massive particles with a tiny momentum exchange. Okay, to actually carry out this expansion, we will do the small q expansion of Feynman integrals involved. This is a well-known problem in the collider literature through the method of regions. I think people have been doing all sorts of expansions for decades, but wisdom was kind of spelled out in a very nice detail in '98 through the systematic formulation of the method of regions by Martin Benecke and Vladimir Smirnov. So then a one-line summary of the method is that you need to identify relevant regions for your integrals. You do the Taylor expansion of your integrand in each region, and in each region you integrate over the entire loop momentum space, and you add up the results to reproduce the true series expansion of your Feynman integral. Thank you. So of particular relevance is the soft region, where this is the region where all the exchange massless particles, like gravitons, have comparable momentum of the order q set by the overall momentum transfer, which is much smaller than your masses. And through the Taylor expansion of the matter propagators, they become linearized propagators, also called Icona propagators. So there are some slight subtleties involved. From the power counting alone, it's not at all obvious that soft region is all you need, because there's the so-called classically divergent or superclassical pieces in your amplitudes. When you expand to the classical order through more than one order of expansion, naively you also need mixed soft and hard regions. So for example, if you actually try to use some automated software like Fiesta 4, it's also possible with PySecDec for automated asymptotic expansion, you will find out that the value of the true integrals expanded to 2 orders in Q need to be reproduced by a mix of regions added together. But fortunately, this complication is not relevant for real physics. We expect that the hard regions to cancel out because there are certain mechanisms in our calculation which cancel these 1/h bar artifacts. To the best of my knowledge, this is kind of intuitively understood, but the rigorous proof is not written down in the literature, and such a proof would be very welcome. Another perspective, which I find illuminating, is the word line formulation, where you perturb against a straight line trajectory b mu plus v mu times tau, with this fluctuation z mu. And from the get-go, you Taylor expand in small z mu compared with b and v. So and if you go through the word line formulation, you directly end up with integrals with linearized propagators, as if you have expanded the exact QFT Feynman diagrams in soft expansion. From this approach, hard region is absent from the beginning. So and once you take into account the expected equivalence between word line and amplitude methods, this is kind of an indirect proof, or at least justification for the fact that you only need the soft region. Now let's further specialize. You can have region, and then you can have regions inside regions, because you can further take limits when the exchange momentum is not only soft, but we also have a small velocity limit where the two bodies are kind of like a non-relativistic system of low velocity. For example, you might want to do this because you might want to do the post-Newtonian expansion instead. But even if you are doing the actual post-Minkowskian expansion, it's extremely relevant because it's used for computing the boundary conditions for differential equations, which we will get to later in the talk. You will need the potential region and the radiation in the small velocity limit. So the potential region, in both regions, the overall scale is still set by this tiny q, much smaller than m. But in the potential region, you have a further specialization of such that the time component is suppressed by the small velocity. So the exchange is dominated by a spatial exchange of momentum, as you would expect from a system that interacts through in a kind of like a non-relativistic potential. And the radiation region can be on shell. So the time component and spatial components are both of order v. Still, this small v, you can think of it like if the velocity v is small, the orbital period will be large. Therefore, the characteristic frequency of this binary system will be small. So this explains the homogeneous v suppression. So yeah, this is just a diagrammatic illustration. The soft region suppresses this q, and then this further splits into potential regions where q0 is suppressed, and the radiation region where both q0 and the spatial components are suppressed. So this has been very powerful in practice, and it also gets a little more intricate at high loop orders. For example, in the 3-loop calculation, which I did with my collaborators in 21, and also in this paper with Dilapa et al. In 23. They analyzed the regions in this diagram in the small velocity limit, and using automated software, it's ASY2.m by Janssen and Smirnovs. You can identify 4 different regions. When you sum them up, you get the small velocity boundary conditions. In its generality, to solve the problem in general is actually an unsolved problem in perturbative quantum field theory. The automated identification of regions, people once believed they can do it through analyzing graph polynomials. They draw the monomials in the u plus f, known as the Lie-Pomeranski polynomial. They draw the monomials as vertices in a polytope They identify the facets of the polytopes to identify the necessary regions. But it turns out that in some cases, this doesn't identify all the regions, and there are hidden regions that you need to dig out. And then there are also recent papers relating to relating the problem to Landau equations in several recent papers. So this is an unfinished story in perturbative QFT, although for the purpose of gravitational wave physics, maybe we know about all the regions already, or maybe there's still some surprise to find out. I will just briefly mention that if you do amplitudes rather than world line, there are some subtleties with this so-called potential region. In that there are unregulated logarithmic divergences. So when we do dimensional regularization, our philosophy is that we never want anything of superficial degree of divergence 0. We want something of whose degree of divergence is something like 2 epsilon or minus 2 epsilon. But strictly degree 0 logarithmic divergence is bad. We don't know how to do it in DAM-REG. So this subtlety arises from the fact that potential regions and radiation regions have the same virtuality. And if you think of dimensional regularization as a smooth cutoff in UV and IR virtuality, it fails to isolate these two regions. Unfortunately, it hasn't been a big problem for us. For example, in 3-loop and 4-loop calculations, we were able to combine the results after IBP reduction at the final, almost close to the final result. We are able to combine certain permutations of vertices, combine integrals with permutations of vertices to cancel these divergences. So I won't get into this more. Now I move on to the second part of the talk, which is integration by parts. So the basic problem is that the kind of Feynman integrals you write down have many propagators and can have many SPs or irreducible numerators. At 3 loops, you get 15 indices, and each index can be different integers. So this just because of combinatorics, you get a mix of many different integrals. At 4 loops, you get 13 propagators plus 9 irreducible numerators. From these 22 indices, you put on allow them to have different integer values. You easily get millions of integrals. And we don't want to evaluate millions of integrals analytically one by one. But fortunately, it suffices to evaluate just a handful of master integrals due to the technique of integration by parts, which was formulated in the early 80s and systematized by the seminal work by Stefano Laporta. So in his work to calculate electron G-2 to very high orders, and his coverage by the Quantum magazine a few years ago. So the Laporta's algorithm has been implemented with all sorts of improvements and variations by many publicly available packages. And so Fire and Kira are probably the two most actively maintained packages that are written in C++ for high performance. So this is a major computational bottleneck. You can have runs that take months on your clusters. Hopefully they don't crash after months, and you get some results back. So there's a big business in improving the methods and going beyond Laporta's algorithm through many approaches that I won't have time to get into. But hopefully in the coming years, they will give us much more powerful techniques to push these integrals much further. So I'll just give a toy example to introduce the Laporta algorithm. For example, this massive bubble integral with internal masses and an external mass p squared. We want to obtain linear relations between integrals with different powers, nu1 and nu2. We just take total derivatives or more intuitively understood as just infinitesimal shifts of your loop momentum measure, and you demand the integral to be unchanged under this infinitesimal shift. So depending on if you shift by k mu or p mu, you get two types of relations. And yeah, you can consider all these different integrals on a two-dimensional grid for the different values of nu1 and nu2 propagator powers. You start with the so-called seed integral, which is what I wrote down here, and applying the IBP operators or these different infinitesimal shifts, you can get IBP identities. For example, here's a 5-term IBP identity generated from this seed integral. Now, your goal is just to come up with a notion of complexity. For example, nu1 plus nu2. So you have these 45 degrees sweeps in complexity. You want to reduce integrals with high complexity living up here to integrals with low complexity living near the origin. And in fact, the 3 master integrals are here. So in the Porta's algorithm, you kind of do it by brute force. You just identify all the seed integrals under a certain complexity cutoff, bounded by your target integral to be reduced. You just look at all the seed integrals and generate all IBP equations. Then you solve this as a huge linear system. In practice, this can be a linear system of millions or even billions of equations. But you solve them on computers, even supercomputer clusters. Then you solve them with Gaussian elimination. So in more complicated cases, the cutoff is generally in terms of number of dots, i.e. raised propagator powers, and the tensor rank, i.e. the degree of the numerator polynomial. So then there's a question of which master integrals to use for your calculation. I think we'll hear more about this from David's talk. So the simplest thing you can do is just to accept whatever master integrals you get from your IBP reduction software. So they will have some implementation-dependent criterion for which integrals are the least complex, which then they are preferred to be chosen as masters. So but in practical calculations, once you go beyond the simplest integrals, it's very beneficial to adopt an improved basis by a pair of papers, one by the Smirnovs and one around the same time by Johan Usovich in the audience. With the improved basis, you get rid of very annoying unfactorized denominators, and your master coefficients will have denominators with factorized dimension and kinematic dependence. So this is essential for obtaining clean results for non-trivial integrals. There's a canonical basis, which I'll mention later in the talk, which simplifies differential equations. And there are also all sorts of finite or quasi-finite bases, which make the integrals finite or finite up to an overall factor of 1 over epsilon in Feynman parametrization. There are also recent papers by these people on how to reorganize IBP equations, the IBP solving procedure, to avoid singularities in the IBP coefficients. So this is an area which, to my best knowledge, hasn't yet been applied to gravitational wave physics, but may be applied in the future. Now, since the IBP reduction is a hugely computationally intensive business, we'd like to optimize it. In fact, in recent 2 years, some of the key work on optimizing IBP has been strongly driven by the needs of gravitational wave physics, in addition to the Collider physics. The basic problems is that you are solving a very large linear system, and in fact over rational functions of your kinematic or Mandelstam invariants and your dimension. A technique which brought a mini revolution to this field is using a finite field and rational function reconstruction methods. The observation is that if you compute with rational numbers, the numerators and denominators in your calculation can easily grow up to be hundreds of digits long in intermediate stages, and that slows down your calculation. If you do your calculation modulo a prime number, you can the numbers always stay bounded by the size of your prime. So in the intermediate stages will become much faster. Sorry. And if you know the image modulo many different primes, you can reconstruct with a very high probability of correctness that you get the actual rational numbers. And then you can reconstruct rational functions by numerical probes through techniques such as Taylor interpolation and Newton interpolation. So in recent years, this has been widely applied to calculations in collider physics, and now we also applied it to demanding calculations in gravitational wave physics. And the advantage of the approach is that things are trivially parallelizable. You parallelize over different primes and different numerical values of your kinematic invariance and dimension. And then another optimization people have looked into is how to improve upon this ad hoc inclusion of the seed integrals, which in one of my previous slides was just a simplistic triangle region bounded by the target integral complexity. So there are several physical intuitions that can help with this problem. I don't have time to go into them, so I'll briefly jump through the next few slides. One intuition comes, personally for me, comes from syzygy equations. People have shown that you can do IBP reduction without seed integrals with raised propagator powers. And if you think about their fancy approach of syzygy equations, their equations are actually linear combinations of the simple equations, simple IBP equations in the Laporta approach. So it implies that in the Laporta approach, you can also survive with seed integrals with no dots, or in practice, sometimes a small number of dots. Another intuition, personally for me, is numerical unitarity. It has been, it brought us the NLO revolution for QCD calculations, and it has also been generalized to loops. And one of the key observations is that you can use master integrands as well as IBP identities to parameterize the loop integrand. And for that to happen, you want your IBP identities to mimic the physical properties of your loop integrand. For example, with a tensor rank that decreases as the number of propagator decreases, as you get fewer 3-point vertices, which can contribute a higher number of momentum powers. So with these considerations put together, we get this improved seeding. So in some early Laporta implementations, the numerator rank, so you need to read from right to left. You keep the numerator rank constant as you go to sectors with fewer number of propagators, and you raise the number of dots or additional propagator powers to such that the number of total propagator powers is unchanged from the top level. But with the previous observations in mind, one possible strategy is allowing the numerator rank to decrease as you go down in the number of propagators, as more and more propagators get cancelled by numerators. This is a little bit of oversimplification. In practice, you may need to impose a lower bound and not decrease it further. And then the number of dots, you can set it pretty much constant to 0, and sometimes just or a little more, like 1 or 2. So this improved seeding strategy, this seemingly innocent change, can speed up IBP by orders of magnitude. I don't want to guess the content of other people's talk, but you may hear about it again in Johan's talk. He implemented in QR3, and we are also experimenting with it in a private version of Fire 7. And we believe these developments will feed into the needs of collider physics via the IBP software. Okay, now I'm go into the final part of the talk about master integrals. So first, I will briefly mention outside the post-Minkowskian world, the closely connected world of post-Newtonian expansion. Recall that we've done IBP. We've written the amplitude as coefficients times master integrals. Now we need to evaluate these master integrals. For the post-Newtonian expansion, the techniques have been extremely well developed to very high loop orders. For example, you have these impressive 5-loop and 6-loop calculations by several groups. For example, involving people in the audience like Ricardo, and also another group by Johannes Blumlein et al. So people have developed many useful techniques. For example, in the static limits, in the odd post-Newtonian power, there are methods to factorize the integral over to lower loop integrals that are easier to evaluate. By the way, I should mention that the main integrals of interest in the post-Newtonian expansion are propagator integrals in 3 minus 2 epsilon dimensions. And one of the useful methods has been dimensional recurrence, for example, by Roman Lee and collaborators. This is some picture stolen from Pierpaolo Mastrolia's slide several years ago. This is a dimensional recursion relation relating integrals in d minus 2 dimensions to d dimensions. And if you allow this d to be a non-integer power, you get a system of difference equations which you can attempt to solve if you figure out appropriate large D boundary conditions for the integrals. And there are also fascinating techniques like the PSLQ algorithm, which allows you to obtain exact results from high precision numerics as applied in this paper to the post-Newtonian expansion. Okay, so historically, the post-Minkowskian calculation has been much harder. For example, the Westphal's calculation in 1985, which produced the second post-Minkowskian result, this corresponds to the O orders in velocity at order g squared. However, if you don't need O orders in velocity, if you only need the first few orders in velocity, people in 1917, just 2 years after general relativity was written down, already calculated this first post-Newtonian expansion, also systematized by Einstein, Infeld, and Hoffman. So historically, this requirement of the exact velocity dependence was a huge burden on calculations. However, in recent years, the method of differential equations has been has revolutionized the picture, and it allows you to promote the small velocity boundary conditions using the same techniques as the post-Newtonian expansion, and then through the method of differential equations, they can be promoted to solutions exact in velocity. So many of the techniques from the post-Newtonian world is again relevant. And in fact, people have been liberally reusing the languages of the post-Newtonian expansion. For example, we talk about results in the potential or radiation regions. We even talk about instantaneous potentials and fluxes, tail effects. None of these things, strictly speaking, make sense if you keep exact velocity dependence in mind. But they have been a very convenient language to relate to certain physical insights. Just a simple illustration. If you have differential equations for the master integrals, and through the IBP reduction procedure, the derivatives will be again, just like the rest of the millions, possibly millions of integrals in your amplitude, these derivative integrals can be rewritten as linear combinations of master integrals. So that's what you obtained as differential equations for Feynman integrals according to these references. And then we work out the post-Newtonian boundary conditions, and we promote them to functions that are exact in velocity. And if you are curious, you can also look at how these functions behave in the ultra-relativity limit. And we will hear, I think we'll hear more about this in Michael Saavedra's talk and Vittorio's talk. Just a little bit of a historical side note. Back in 2019, where we published the third post-Minkowski order calculation, which finally obtained the next order after Westphal in 1985. There was an incomplete first attempt of using differential equations. We obtained the differential equations for the only a subset of diagrams without iteration, for example, the H diagrams. When we wrote down differential equations before the soft expansion, then we took the soft limits of the differential equation matrices as well as their boundary conditions. The procedure is a little bit overcomplicated, but I provided useful cross-checks. And 1 year later, with my collaborators Julio Paramartinez and Michael Roof, we have a much cleaner formulation for amplitude-based PM calculations. We rely on doing the soft expansion in advance, and we only target these soft expanded integrals, which depend on only one non-trivial variable, which is the velocity variable. So you can really think about a differential equation in velocity that takes static boundary conditions to exact in velocity. And we also introduced a convenient variable, which, of course, we benefit from the Kleider literature, where people routinely do these things because they need to rationalize square roots in differential equations. And this variable has been adopted as standard. So yeah, I'll just flash a very small toy example. For the soft expanded box, in fact, this is even simpler than the massless box example you see in quantum calculations, because there are only two master integrals in the soft expansion. You have the soft master, and you have the box master and the bubble master. The triangle master completely decouples due to some parity in the power counting. So we normalize the master integral with appropriate powers to simplify the differential equation, more precisely to target the so-called canonical form by Johannes Hahn. And we get a very simple differential equation. And then if we solve the differential equation, depending on the boundary conditions, you either get the full result log x minus I pi, or the region or the potential region result, which is simply constant. And then you can assemble these integrals into amplitudes to obtain results for the second post-Minkowski correction. Now, I should mention that we also need phase-space integrals, not just loop integrals. For example, if you look at the Kosawa-Maybe-Okano formalism, one of the authors is in the audience. You need both linear and quadratic pieces of your amplitudes in the classical observables. In the quadratic piece, you have the amplitude times Fourier conjugated amplitude, and you will have these delta functions. So fortunately, the delta functions, these cut propagators, can be just viewed as almost the same as usual propagators, but with a modified integration contour or epsilon prescription. For example, if you just integrate with a circle around the pole, you just get a delta function rather than the Feynman propagator. I should mention that similar issues also arise in Waldline formalisms. The Waldline formalism is very close to just solving classical equations of motion, and you naturally get retarded and advanced propagators. And again, the integration by parts and by extension differential equations are insensitive to the I epsilon prescription. So the IBP and differential equations become unchanged, although something has to change, and that's the boundary conditions. In the Kleider literature, this has been extremely powerful in calculating Higgs production total cross sections For example, back in 2014 or 15, there's this famous paper in the Clyde literature which pushed Higgs production total cross-section to the unprecedented 3-loop order, and they essentially relied on the reverse unitarity method to handle all the phase-space integrals. As an example, in our paper, which calculated the total energy loss in the scattering of 2 black holes, these are some of the integrals that are involved. And with reverse unitarity, the phase-space integrals have been pretty easy to solve, which allowed us to obtain the energy loss at the leading order in G, which is a G cubed order. It's a fairly high order because you cannot radiate unless you start accelerating. But still, this is the leading order for this particular observable, which is the radiated energy. So people looked at this back in the 70s, and essentially they had the integrand, which is fine for like the actual waveform, but this seemingly innocent additional step of performing the phase-space integral to get the total energy was a little bit of a trouble for them, and actually they got the wrong numerics. But with the reverse unitarity method, this is almost like a student's exercise, and we get a very clean analytic results. Also agree with non-relativistic expansion to very high, like the 15th order by Bini, Damour, and Gerardico. Okay, so one very powerful form of differential equations is the canonical form, where the right-hand side of the differential equation is proportional to this dimensional regularization parameter epsilon, which allows you to solve the differential equations order by order in epsilon by definite integration in terms of multiple polylogarithms, which are applied in many modern amplitude and Clyde calculations, for example, in Andrew's talk. And people have devised many strategies for finding a good master basis that land you onto the canonical basis of differential equations. And many of these methods have been tremendously useful for our calculations. So at 3-loop orders, we actually need to go beyond the canonical form and the polylogarithmic solutions. One of the many ways to see the problem is through the Picard-Fuchs operator. The original form of the differential equations, I wrote down an ODE for n master integrals, a linear ODE, and you can easily turn this into an nth order differential equation for just a 1 master integral, and this gives you the Picard-Fuchs operator, and in cases that you get Picard-Fuchs operators that cannot be factorized into linear differential operators, you know that you will get sophisticated special functions beyond polylogarithms, and this is first encountered at 3 loops. And I'll just flash the 3-loop result. For example, from the 21 paper, there were also independent worldline calculations later in the year by Rafael Porto and collaborators. We have a mix of polylogarithmic solutions like Li2. Here we have this arc-cosh. If you adopt variables that rationalize these square roots, these arc-cosh are simply logarithms. But you also have these complete elliptic integrals k and e, and at higher orders you will get even more complex functions like iterated elliptic integrals. Now at 4-loop order, and I won't go into any details, but in recent 2 years, people have found many fascinating things. For example, in these papers, which look at the geometry of maximal cast and Picard-Fuchs operators, people predicted that you will get Klabi-Yau periods as integrals appearing in your post-Minkowskian predictions. So a complementary perspective to Picard-Fuchs operators is the geometry from the leading singularity, for example, computed from the Bykov parametrization, which is a parameterization that trivializes the cut structure of Feynman integrals. You get square roots of a high-degree polynomial integrated over several variables, and you cannot iteratively take unit residues, as in the polylogarithmic case, as some people know very well in, for example, n equals 4 super Yang-Mills amplitudes. Okay, and in fact, a group mainly based on in Humboldt in Berlin, also involving Johann Usovich in the audience. I think you will hear more about it in Johann's talk. They confirmed that these Calabi-Yau integrals in fact appear in final results. If you look at the dissipative part of the fifth post-Minkowskian results, truncated at the first self-force order. And here's a tally. I think I won't go into this long list, but there are some interesting patterns. At two loops, you get weight 1. There's some transcendental weight, well known in the literature. There's some notion of transcendental weight. Logarithms has transcendental weight 1. At 3 loops, you start getting transcendental weight 2, like these Ly2 functions. At 4 loops, you get transcendental weight 3 in the multiple polylogs. Very curiously, if you go to a special supersymmetric theory, but still truncated at the first self-force order, you only get weight 2 polylogs, and restricted to be in a very special class of multiple polylogs called harmonic polylogs, with a very small set of symbol letters. So, and in the potential region for the supergravity, at the second self-force order, which is all you have at 4 loops, we obtained, we see non-trivial cancellations of boundary integrals that tag elliptic and Calabi-Yau integrals, and which seems to suggest that only polylogs will survive in the final result. This kind of cancellation also appear in the 3-loop calculation. There are some cancellation we don't really understand, and it will be very interesting to see what happens for the holy grail of the maybe next few years, the 2SF general relativity. We hope we will find out the answer with the help of supercomputers. And I don't have time to mention, but 4-point integrals are, of course, not the end of the story. And if you want certain observables like waveforms in the scattering events, you need to compute 5-point integrals. And here, from a technical Feynman integral perspective, the main difficulty is that you get many more kinematic variables. There are 5 independent kinematic variables instead of just 1 for the 4-point integral after you do soft expansion. Fortunately, at 1 loop, things are pretty well under control, and the 1-loop waveform, in the 1-loop waveform, the most complicated special functions are your usual friend of just logarithms. This is in the frequency space, in the Q space. To actually get a prediction for black hole scattering with a definite impact parameter, you need to do a Fourier transform, and this has become another frontier in multi-loop calculations, which is adapting the technique of IBP and differential equations to do Fourier integrals. And people have observed many neat things like iterated integrals with Bessel function kernels. Okay, this brings me to the end of my talk. So the modern amplitude methods, such as generalized unitarity, double copy, and effective field theory, combined with the integration methods developed in decades in the QCD and Collider literature, revolutionize the post-Minkowskian expansion in gravitational wave physics. And this is seen by the fact that it took us more than 30 years since the result of Westphal in 1980s to reach the 3rd post-Minkowskian order, but only 2 more years to reach the 4th post-Minkowskian order, and just a few years after that for people to get first partial results in the self-force truncation for the 5th post-Minkowskian order. So this really caused the field to revive and explode. This relies on many Feynman integral techniques like the method of regions, integration by parts, and differential equations. So in reverse, I believe the demands of the gravitational wave physics has also been pushing the state of the art in Feynman integral computation technology itself. For example, people arguably have the first physically relevant application of Calabi-Yau integrals rather than just practice calculations like things like multi-loop banana integrals. And the demands of gravitational wave physics has also been pushing the IBP reduction software on a scale that can be used on supercomputers. There are many, many open problems. For example, for people interested in predicting the analytic function space in amplitudes, the question is, what controls the function space in GR and supersymmetric theories? Why do elliptic integrals seem to cancel in supergravity? And even in GR, we have seen preliminary evidence that, we have preliminary progress that, for example, in the 1SF truncation, the conservative part has seen remarkable cancellation of Calabi-Yau integrals, although in the dissipative part, it appears again. So we don't really have a good understanding of when interesting functions show up. And given the enormous progress of the experimental front, we want to push to higher orders. How would we do that? And then we talked about the low and the small velocity limit. And how about a high velocity limit? What can we do about it? You will hear more about it later in the conference. And finally, the QCD literature has many numerical integration methods, and can we benefit from that? Thank you for your attention.
Yeah, thanks, Mao, for that really great summary and overview. Do we have any questions? Yeah, please.
So about the second point, can you comment more about what's the biggest problem? Because, yeah, I would like to understand better this.
Sorry, second point?
No, in the conclusions. The 6 p.m., so what's the problem with the, like, you said, overcoming IBP bottleneck?
Yeah, it is. So I didn't have time to mention, but already at the current frontier, which is the 5th post-Minkowskian order, the IBP reduction calculation has been very time-consuming, and we've been applying for supercomputer hours for this purpose. And given that we expect one more loop order to bring an additional increase in computational burden, the IBP will become maybe prohibitive with the current technology. So new developments will be essential.
Yeah, hi Mao. Thanks for the nice talk. So in the beginning you mentioned the hidden regions and Newton polytopes. Did you see any hidden region, or do you expect to see any hidden region at 6 p.m. or in the classical limit we can access all the regions?
I mean, I mentioned this mainly because that many regions we assume are not proved in a rigorous manner. However, based on the intuitions around post-Newtonian expansion, etc., I more or less think that probably potential regions and radiation regions are all there is, but things are much less clear if you go to the opposite region. For example, the high energy limit, which people have been starting to look at. There are interesting things like global regions that can be relevant, and do you really have a full classification of all the necessary regions? Maybe there's something to benefit from the literature on like finding hidden regions.
Right. Thank you.
Mao, when you discussed the regions at the beginning,
Yeah.
You said that essentially Q, the momentum transfer, must be smaller than the square masses, right?
Yeah.
Okay, I just wanted to make a comment. What then Michael and I will be discussing, which we can call high energy limit, will really be the Reggie limit, which means S much larger than T, the momentum transfer,
Yeah.
and the square masses of T.
Yeah.
Okay, the same as T.
Right.
Now, an order where S is much larger than the square masses, and those are much larger than T,
Yeah.
okay, is a forward limit, but it's not the Reggie limit that we'll be dealing with. However,
Right.
we know as a fact from the computations that you guys have done at 2 loop, 3 p.m.,
Yeah.
and the detailed analysis that Di Vecchia, Heisenberg, Russo, Veneziano have done,
Yeah.
that for the leading logs, it makes no difference at all.
Yeah.
Namely, okay? So you get the same logs whether you take the masses to 0 or you actually have the masses in,
Yeah.
okay? So just as a comment, it would be quite interesting to explore this in detail at 3 loops,
Yeah.
4 p.m., to see what differences there are in the logs and in the leading power terms between the forward region, which is no Reggie region, and the Reggie region, okay?
Yeah, thanks for the comment. I fully agree. I think at the 3 loop or 4 p.m. order, there's some interesting divergence we need to understand.
Thank you.
Hello, Mao.
Oh, hi.
Many thanks for this very compact, dense overview. You covered many things, which saves time for me. Fantastic. I like what you said about hidden regions. So how did you study them? Did you develop like F and U polynomials?
I think what people do is that they look at this.
No. What did you do?
Oh, okay. I didn't have to do it so far because this potential region expansion has worked so far, but
I see. So how I see it is, if you develop F and U polynomials, what I see, they are all positive definite. So there's no room to create hidden regions, which is nice. Unlike in QCD, where you have like alternating signs and so on. Okay, I have another selfish comment. I think you forgot my name on one of the slides, where you mention this method of better seeding.
Oh, okay.
Yeah.
Let me.
Because then, not a selfish comment on the 6 p.m. calculation.
Sorry, the seeding slide or.
Yeah.
Oh, okay.
No, do not waste time now. Okay, and then there's another comment on the 6 p.m. I think that's this improved seeding that has still room to improve. I think we can still go for another order of magnitude. The question is, can we reach then 6 p.m.? Is it just one order of magnitude away?
I think you.
Yeah, there's.
Yeah, okay. I need to insert it here.
Good.
So sorry
Thanks.
for that. So you believe you can further improve the seeding?
Yeah, I think so. Because if you look at the spanning cut idea, we see that it goes one order of magnitude better, and we could achieve it also with better seeding.
Okay.
I'm sure.
Yeah, I fully agree with this. And there are also some papers I didn't mention, like trying to apply machine learning ideas. And in some cases, they can marginally improve upon the state of the art. So, but a huge improvement will be very welcome.
Yeah, but we need like order of magnitude at least improvement.
Okay, thank you.
Thanks, man.
So now I have another question. Regarding the n=8 computation, I mean, you also have massive scalars minimally coupled to gravity there, right?
Yeah.
Now, it's just a question, I don't know. I mean, in n=4, there is no analog of this restriction of the alphabet to X and 1 minus X to HPL kind of polylogs?
Okay, so it might be also because of the 1SF restriction. So it's just that at 1SF, which is a simpler piece, you only get harmonic polylog. And also there's a reduced weight of only weight 2, which didn't increase from 3 loops. At 2SF, probably you will get weight 3 and maybe a full alphabet. So
Okay, okay. So it could just be an accident of the partition in the masses,
Yes,
essentially.
yes.
Okay, thanks.
Yeah, I think it's time to move on. We've had plenty of questions. And let's thank Mao again for that wonderful talk. There's our next speaker. So our next speaker is John Joseph Carrasco. And I guess let me